Sister Muruganandam, take over.
Yeah.
Can I go ahead?
Yeah,
Okay. Welcome to you all for this year-long series of panoramic lectures on harmonic analysis and representative theory. And today in our midst, we have Professor Narayanan, who is giving a series of lectures on the Harish-Chandra proof of Plancherel Theorem and SL2R. This is his fourth lecture. I invite him to deliver that.
Okay, thank you very much. So let's continue. I'll quickly recall what we have been doing so far, and then continue with the classification. And well, I hope to finish the classification of irreducible unitary representations of SL2R today. Okay, so recall that we have G, which is SL2R, and pi V unitary irreducible representation of G. So V is a Hilbert space and pi is a unitary representation. Then first thing we did was to decompose V with respect to the action of K, the maximal compact subgroup. So that was direct sum Vn and in Z. Some of the Vn's may be 0. So we proved that dimension of Vn is less than or equal to 1, right? Then we also showed that these Vn's, so the algebraic direct sum, so that's what we called V sub k, the k finite vectors. So V sub capital K. So this is the algebraic direct sum of Vn's that appear there. Those are real analytic vectors. Okay, so contained in 20, contained. Okay, so these are analytic vectors. Okay, and these are smooth vectors, C infinity vectors. And consequently, V omega is dense in V, right? That is where we are. And then we looked at the K types that can appear in this decomposition. So that is what we call J pi. So recall that J pi was all those K types that appear in the decomposition of pi restricted to the maximal compact. So this is all those n such that dimension of Vn is 1. Right, then we looked at certain vectors, certain differential operators that come from the universal enveloping algebra. One was the Casimir. So let's recall that omega Casimir acts like a scalar, because pi is reducible and omega comes from the center, and we denoted it by q, right? So q is a number with respect to which omega acts. Then we had certain properties of this K types that appear, right? So one, J pi consists of integers of same parity. So you will have either even integers or odd integers. 2, J pi, the K types that appear is an unbroken chain. Okay, so J pi is an unbroken chain. And 3, if Vn is not 0, so that means nth K type is non-zero, then Vn minus 2, that is you are going to the left, that is 0 if and only if q equal to n into n minus 2, and Vn plus 2 is 0 if and only if q equal to n into n plus 2. Okay, so these things follow immediately from those formulas we had written down for those vectors x alpha and x minus alpha and h bar, right? So we had 3 elements from the complexified Lie algebra which gave us these relations. Okay, so we continue analyzing these K types. We'll get some more information. So let me write down this as a theorem, and then we will see how to how this will lead to a classification. Okay. So phi v is irreducible and unitary. So this is something which we'll always keep in mind. First assertion is that suppose J pi is even type, okay, or odd type, right? So it has to be either even type or odd type, meaning it is either even integers or odd integers. Okay. Okay. If q is not equal to n into n minus 2 for any positive, even, or odd integer n. So remember, this is positive. Then J pi is doubly infinite. J pi is doubly infinite. So remember that it is an unbroken chain, and when we say q is not equal to n into n minus 2, that means for a positive integer, well, positive or negative, it doesn't matter. So I'll come to the proof in a minute, and proof is sort of straightforward. Okay. Suppose J pi is even type or odd type, and q equal to n into n minus 2 for some even or odd positive integer n, then there are three possibilities. One is J pi, so it can start from somewhere and go to the right. So that is n plus 2, n plus 4, and so on. So remember, the n is positive, okay, but J pi could be, it goes to the left. So I have minus n minus 4, minus n minus 2, minus n, and it goes to the left. Or it could be a finite thing, minus n plus 2, etc., n minus 2. Okay, so there are only three possibilities. So let us see why it is. So this is easy to see. Sorry. To prove. So look at A. If q is not equal to n into n minus 2, right? So we are assuming that q is not equal to n into n minus 2 for any positive integer, right? So if q is not equal to n into n minus 2, then q is also not equal to m into m plus 2 or m minus 2 for any integer. Okay. Why is that? Because if I change n, if I write n equal to minus L or something, right? Minus L, then n into n minus 2 is minus L into minus L minus 2, that is L into L plus 2, which is also of the same form, right? So this is, if this is k, then this is k minus 2, right? So it is of the same form. So if you can write q as n into n minus 2 for some positive, and then you can also write q as n into n minus 2 for a negative n. Okay. So that is something one should keep in mind. So this means if I have some n here, let us say positive, and Vn, so Vn survives and Vn plus 2 or Vn minus 2 does not survive, then you look at the symmetric part here, and you cannot go further, okay, because the reason for Vn minus 2 or Vn plus 2 to be 0 is same when you go to the other side or this side, okay. And that is the reason this restriction for the k types to appear will happen. Either it is on the positive side or at the negative side, or it is doubly infinite. Okay, so if q is not equal to n into n minus 2 for any integer, so this would imply all Vn's exist, right? All Vn's exist. but then it is an unbroken chain and it goes to both sides. So it is either all positive, all even integers, or all odd integers, right? So we have that. Similarly for V, so the issue here is I'm looking at q equal to n into n minus 2 for some positive n. Then I want to say only 3 possibilities appear, which means you start with an n which is positive and go to the right? So you have n plus 2, n plus 4, and so on. Or you start with a negative n, right? So minus n, and then you go to the left, minus n minus 2, minus n minus 4, and so on. You cannot start from, let us say, minus 10 and then go to the right. Okay, you cannot start from minus 10, minus 8, minus 6, etc., and then go to the right. Because whatever condition happens at minus 10, so that V minus 12 is 0, will again happen at 10. Okay, and then 10 plus 2, 12 will not be, V12 will not be there. Okay, so you cannot start from the negative side and then go to the right to the positive side. You have to start from the right side and then go to the right side. Similarly, when you start from the negative side, you go to the negative, to the left. Okay, otherwise you will have a finitely many k types, right? You start from, let's say, minus 10, V minus 10, V minus 8, etc., but then you will die at V10, right? Because the condition that q equal to n into n minus 2 will be satisfied at V10, and then we will not have V12 onwards. Okay, so these are the only 3 possible. You can't have broken chains, right? So if I break it at 10 and then I start again at 14 or so, then you have 2 submodules, right? And you are starting with an irreducible representation, so it cannot happen. Okay, so this J pi being finite, that gives me a finite dimensional representation, but that tells me there are no finite dimensional unitary representations of SL2R. So this will not appear in our classification. Only these 2 will appear. Okay, so these 2 will correspond to discrete series, and the doubly infinite case corresponds to principal and so principal series and complementary series. Okay, so that is how it is going to look like at the end. Okay, so let us continue. I hope this much is clear. So maybe B similarly. Okay, so let's make a definition. So again, all these are infinitesimal data. Okay, that is something you should keep in mind. We are looking at the k-finite vectors. So the k types that are appearing in a representation. So this is decomposition with respect to k. But then we know that the Casimir acts like a scalar, and that is an additional value q we have. And the theorem is again something which we will not get into the proof of, is that this data is enough to determine the representation. Okay. So let us make a definition. 2 unitary representations, phi and phi prime, are said to be infinitesimally equivalent. So this would simply mean that they are equivalent with as representations of UGC. Okay. If pi v sub k, so those are the k finite vectors for pi, and phi prime v k prime. So these are the k finite vectors for pi prime, are algebraically equivalent. Okay, that is there exists a linear isomorphism. Let's say T from the vector space V sub k, these are k finite vectors for pi, to the vector space V sub k prime, which is the k finite vectors for pi prime, such that so this is an invertible linear transformation which intertwines the action of pi and the representation of the Lie algebra, right? So the pi dot and pi dot prime. Okay, so that's the T pi dot x equal to pi dot prime x t for every x in the Lie algebra, of course, if it is true for every x in the Lie algebra, it goes for every operator in the universal enveloping algebra. Okay, so the corollary, if you like, of the previous, so there is something to be proved in the corollary, which I will not get into. But this helps us in classifying. So let pi and pi prime be unitary irreducible. Then pi and pi prime are infinitesimally equivalent. If and only if q equal to q prime and j pi equal to j pi prime. Okay. So the data which we have, j pi and q, right? So the q is the scalar with respect to which the Casimir acts. J pi is the corresponding k types, right? All those vn's where n vn's appear, right? So dimension of vn is 1. So these two data is enough. Okay. So there is a small proof one has to do here. I am not going to get into. So if j pi is equal to j pi prime, one way is trivial. If pi and pi prime are infinitesimally equivalent, then this tells me that t intertwines pi dot omega and pi prime dot omega, right? And so the value of omega, the Casimir in both the representations will be same. And of course, the k types will be same again because of t, the intertwining operator. It is the other way which is slightly non-trivial. If I know q and q prime are same and j pi and j prime are same, we need to show that pi and pi prime are infinitesimally equal. See, j pi and j prime are same, meaning the k types appearing are same. So let us say j pi consists of just the even integers, okay, and j prime also consists of even integers, all even integers, right? So for each vn, we have, it's a one-dimensional, right? So you can map vn to the corresponding vn prime for pi prime, right? So that is fine. But then you have to make sure that it is an isomorphism. So there is a certain there's a certain choice you have to make and say that it is actually an isomorphism. Okay, so there's something to be done there. But yeah, okay. So now let me write the conclusion as a theorem. If pi and pi prime are unitarily equivalent. Okay, so let's take two representations. Okay, so let pi and pi prime be two unitary irreducible representations. Then pi and pi prime are unitarily equivalent. So that means as representations of G, right? As representations of the group G, they are same. If and only if pi and pi prime are infinitesimally equivalent. Okay, so that is as representations of UGC, right? Or G, which we know by the corollary happens if and only if q equal to q prime and j pi equal to j pi prime. Okay, so again, here also there is some proof to be done, except especially for the unitary equivalent. So two representations unitary equivalent means you have to produce a unitary operator which intertwines the representations, right? So again, it's easy to see what needs to be done, but there is a choice to be made, right? Because the vn's are same, the k types are same, and if they are unitary equivalent, the k types have to go to the k types, and k types are one dimensional. Okay, so you can take a vector here in vn and map it to one vector in appropriate, say, let's say orthonormal vector in vn prime. Okay, but there is still some choice to be made. You can multiply by any complex number of modulus 1, right? Even that would, so you should be able to choose that appropriately. Okay, so that requires some computation, but otherwise the proof is not very difficult because the VNs are one dimensional. In the general case, of course, it's a much more non-trivial theorem. Okay, so this sort of classifies the representations in some sense, at least in the infinitesimal sense. Okay, now to complete the classification for unitary irreducible representations of SL2R, what we do is the following. First, we look at the list. So we have a list of unitary irreducible representations. What are they? One is the principal series, right? There are two sets of principal series, and there is the discrete series and the complex conjugate of it, that is the anti-holomorphic discrete series and the holomorphic discrete series, and there is the complementary series, right, and trivial representation, if you like. So these these set of representations, so they come with the data, right, the J-pi and the Qn, and since these representations are explicitly realized on function spaces, these can be computed, and one knows the values of Q and J-pi. I will explain this a little bit more as we go along. But how do we say they are all? So I start with any irreducible unitary representation of SL2R, let's say pi. So I have J-pi and Q, right? Now, so we'll take one example of J-pi and then say that Q has to be in certain range. Okay, so that will follow from whatever we had done for those x alpha, x minus alpha, and that computation. So that computation will tell us that the range of Q, the Casimir's eigenvalue, has to be in a certain interval, or it has to be less than 0, greater than 0, something like that. But then we can look at the list and see that there is a representation which matches the infinitesimal data given by it. Then they have to be same, right? They have to be unitarily equivalent by whatever we have done, right? So all we have to do is to look at the infinitesimal data and match it with whatever existing data we have. If they coincide, then we are done. Okay, so that is what we will be doing. So first, let me give you the list of representations. Okay, so to complete the classification, we first list a set of unitary irreducible representations. Unitary irreducible representations of G. Okay, so this I had done earlier, but I didn't explain much about this representation. So I'll try to do this in few words. Okay, so one, pi lambda in R. This is the principal series. Okay, and you also have pi lambda minus for, so these are all unitary irreducible. Okay, unitary irreducible. Okay, and the equivalence is pi lambda is equivalent to pi minus lambda. Okay, we also have pi lambda minus, so that is another set of irreducible representations. I'll come to the construction soon. Okay, I won't write down the explicit expressions. It is possible, but it will not give us any new insights to what we are doing right now. Lambda in R minus 0. Okay, this is also principal series, and we also have, so these are unitary irreducible again, unitary irreducible, and the pi lambda minus is equivalent to pi minus lambda minus. Okay, so they are equivalent. Now so here there is a missing piece 0. So pi 0 minus is not irreducible. Okay, that becomes the sum of two representations called d1 and d1 minus. Okay, so let's say d1 plus and d1 minus. So these are called limits of discrete series. limits of discrete series. Okay, so that is one set of representations. So let me say a few words about how these representations are constructed. So recall that we had the minimal parabolic. So construction P equal to MAN. So this was the minimal parabolic. Minimal parabolic. What was M? M was plus or minus identity. A was those matrices e to the t, e to the minus t, and maybe there was t by 2, t in t positive, because that's the connected component, t positive. And n was nilpotent, right? That is all 1, let's say x, 0, 1, right? X in all. Okay, so A and N appeared in the Iwasawa decomposition K, right? So same A and N. M is actually the centralizer of A in K. So it's a subgroup of K. That is the general definition. In this case, it's just plus or minus identity. And MAN is a group. So this is the group of upper triangular matrices. Upper triangular matrices in G. Okay. Now, what you do is you take a representation, take a character of MAN and induce. Okay, so M hat is trivial. So there are only two representations for M, right? It's plus or minus identity. So it's trivial and let's say signed representation. Okay. Now, what you do is, and okay, A. So A hat can be identified with the real line, right? I take a lambda in R, then I have the character rho lambda, AT equal to e to the I lambda t. Right? That is a unitary character of A. And so you take this representation, which is, so let's take sigma in M hat and lambda, let's say rho lambda in A hat. Okay. And look at sigma tensor, rho lambda tensor trivial. Okay. So let's call that 1. Okay. As a representation of MAN. Okay. Equal to P. That is what we generally do. Now, well, we can prove that this is actually a character. This is a one-dimensional representation. It's a character of MAN, and then you induce. Okay, so the pi lambda sigma is the induced representation from P to G of this representation sigma tensor rho lambda tensor. Okay, so in my notation, sigma trivial, then I have pi lambda. Sigma sign representation, I have pi lambda minus. Okay, right? These are the two representations I have, pi lambda and pi lambda minus. When I say pi lambda, the sigma is trivial. So I'm simply inducing from trivial tensor, rho lambda tensor trivial. Pi lambda minus meaning I'm putting the sign representation. Now, from the way these things are defined, one knows that, pi lambda is realized on, pi lambda is realized on a suitable function space on G by P. So G by P, so that is how you induce. Okay, so so maybe one word about induction. So I have, let's say I take a representation rho of P and I induce, right? So let's say pi equal to induction, right? From P to G of rho. So what does that mean? I look at all those functions from, so appropriate functions. So there is an L2 condition and all that, which I'll not bother into, which I'll not bother too much about. So G2, let's say V rho. So P, rho of representation of P on V rho. Okay. So you look at all those functions which transform according to the rho. So f of G, let's say P equal to rho P inverse f of G. Okay, this collection of functions which are in L2 and all that with respect to some measure. One problem here is that G by P does not have a G invariant measure, but one knows that there is a unique measure class which is quasi-invariant with respect to G action, and you can take one such measure. I'll come to that soon. And here you can define your representation pi G acting on F at X would be F of G inverse. That is just the left regular, but since there is no invariant measure, you have to multiply by something. Okay, so pi of G acting on F at X equal to some quantity to the half times F of G inverse X. That quantity is precisely the Radon-Nikodym derivative. Because there is no invariant measure, but if I hit it with G, it becomes a absolutely continuous, mutually absolutely continuous measures, and there is a Radon-Nikodym derivative. You put the half of the square root of that. Okay, so then it becomes a unitary representation, because the L2 in the L2 condition, the G inverse will come, and then that action brings in the Radon-Nikodym derivative, which will get cancelled here and so on. Okay, so that is how it is realized, and there is an explicit way of writing it down. So one way to look at that would be G by P is this is K by M. Okay, and so this is a compact space, so you can think of it as a circle with antipodal points being identified and so on. And if you look at the trivial representation, when rho is trivial, so here there is no change. So because of that, you will be looking at L2 functions on the circle which are even. When you take the sign representation, you will get L2 functions which are odd. Okay, so pi lambda is realized on, pi lambda acts on L2 of the circle. So let's put T even, which means that in our case G pi lambda. So J pi lambda, the K types that appear, that are just 2Z, right? All even e to the in thetas where n is even. And similarly, pi lambda minus, if I look at the construction, it is easy to see that it acts on L2 of odd functions. And here J pi lambda minus would be the even ones, the odd ones, 2Z plus 1, right? So those are the K types that appear for the principal series, the two sets of principal series. For one principal series, it is just the even integers. For the other, it is odd integers. And in both cases, one knows that the Q value, Q equal to, well, the way we have defined it is probably minus lambda square plus 1 by 4. Okay, and so it is less than or equal to minus 1 by 4. Okay, lambda is real, right? So Q we have defined the Casimir as a So Casimir you should be careful about. It's a symmetric operator, so it has real eigenvalues in some sense. So you can have minus and positive. Okay, and so here the Q value will be exactly minus 1 by 4. Okay, so that takes care of the principal series. The second one is the discrete series. So there is dn plus and dn minus. So one is the holomorphic discrete series. So this is holomorphic discrete series, and this is the anti-holomorphic one. Again, you can write down explicitly how it acts on a set of function space. So you can think of holomorphic functions on the upper half plane, which are square integrable with respect to a certain weight, which is y to the n minus 2 or something like that. Similarly, you can bring everything to the disk. So remember that SL2R and SU11 are same groups, and SU11 acts on the unit disk, and you can look at holomorphic functions in the unit disk, which are in L2 with respect to a certain weight. Okay, so for each n there is a weight, something like 1 minus mod z squared to the n minus 2, and then you have a certain G action. So that is like the usual Mobius transformation action multiplied with a certain weight. Okay, so this again is a very explicit construction. And well, limit of discrete series is d1 plus and d1 minus, which appeared in the decomposition of the principal series pi 0 minus. And here also one knows the k types that are appearing. So that is dn plus, this is n plus 2, n plus 4, and so on. So remember, this was one of the possibilities when we analyzed J pi, right? And similarly for J dn minus, this is the other side. So I have minus n minus 2, minus n minus 4, etc. Okay, so that is the k types that appear in the case of discrete series, and q is of course n into n minus 2, right? That is when the J pi becomes one-sided, right? Otherwise, it's doubly infinite, which is what happened in the principal series. 3 is the complementary series. So I will not bother about this at all because this doesn't appear in the Plancherel theorem. But this is a very interesting construction. So if you look at the construction of principal series, we induced from certain unitary character of the minimal parabolic, right? Instead of this, you can take any character of A, right? Instead of taking lambda in R, you can take lambda in C. That's also a character of it. It's not unitary anymore. And then it's possible to induce, and you will get a representation, that you will get an admissible representation of G. Now, for certain values of lambda, which is not the unitary character, it is possible to change the inner product. So the inducing construction comes with a certain definitions, right? But it's possible to change the inner product, the Hermitian form, to make the induced representation a unitary representation. And that is for a certain small interval of lambda. Okay, so that also gives us some representation. Okay, so complementary series. So that is denoted by Cu, 0 less than u less than 1. Of course, this is sort of meaningless because I'm not telling you how Cu acts. Okay, but it's so this think of this as essentially the principal series, but not from a unitary character of the minimal parabolic. But at the top, you change the inner product. Okay, and the Q value is between minus 4 and 1, 0. Okay. All right. So, and of course, we have the trivial representation as well. Okay, so I won't bother about this much. Trivial representation where Q is of course 0. So this is the collection of unitary reducible representations of G, which we can construct by hand. Now, our aim is to show that any unitary reducible representation of G is actually one of these, right? So that is the conclusion. Okay. So to conclude, we show that any unitary irreducible representation phi of G is one in the list. Okay. Now this requires some computation, so I'll avoid that, and I'll tell you what the idea is. Okay. So let's take one such pi. Okay. So unitary irreducible of G. We want to say pi is unitarily equivalent to one of the principal series, discrete series, or complementary series, right? So let's take J pi. So J pi is the collection of k types that are appearing. So let's take, for example, this is 2 times set. That means, let us say it is doubly infinite and all integers. So this is for example, okay, to fix ideas. Assume this. Right? Because we know the possibilities. We know that J pi is either all even integers, all odd integers, or you start from n positive and go to the right, or start from minus n negative and go to the left, right? These are the only possibilities that we already know. So let's take one possibility, 2 set. So our Vk is going to look like V0 plus V2 plus V4, etc., etc. And similarly to the left, V minus 2, V minus 4, etc. Right? And these are all one dimensional, right? All the Vn's are one dimensional. So there is a V0 here, which spans that. And similarly, let's say there is a V2 here, and there is a V minus 2 here, and so on, right? Those are the vectors in those spaces which spans your space. Now, we recall this computation we did earlier with the operators x alpha and x minus alpha. So let me write down that. Recall that x alpha, x minus alpha to the L acting on V. This was 1 by 4 Q minus n minus 12, n minus 12 plus 2, x alpha L minus 1V, right? So this was for V in Vn, right? The n comes here on the right hand side, right? Similarly, the other way, x minus alpha, x alpha to the LV. This was also the same expression, except that n minus 12 becomes n plus 12. N plus 12 plus 2, x alpha, yeah, here it is minus, here it is L, right? So that is how this is something which we had proved by induction. At least we showed one step. Now our aim is to, so I start with j pi equal to 2z. My aim is to show that q value has to be whatever is there in for principal series or complementary series. For complementary series, the q value is between minus 4 and 0. For principal series is less than to minus 1 by 4, sorry, not 4. So the q value stays below 0, right? And all the values from 0 to minus infinity is taken. So if I can show that the q value lies in that range, 0 to minus infinity, then q value will coincide with one of the principal series or the complementary series representation. And the k types coincide, right? Because the k types for complementary series and the principal series is just 2z or 2z plus 1 in the other case. So the infinitesimal data will coincide, and so the representations will have to be unitarily equivalent. So that is all we have to do. Okay, so that is a simple computation. So let me show this in one case. So take V0 in V0, capital V0, okay, and look at x alpha V0. So remember, x alpha increases the weight, right? So Vn will go to Vn plus 2. So x alpha V0 will be in V2, right? So the norm of V2 square, so let's look at that. This by definition would be the inner product of x alpha V0 with itself, right? So I have not done anything. Now you bring x alpha, one x alpha to the left, it will be its adjoint, then you can prove that it is minus x minus alpha. So that is minus x minus alpha x alpha V0 V0. Now you see, this is precisely what we have written down here, right? So you can compute that. So I'll write it down. So this is simply minus 1 by 4 times q minus 2 into 4 V0 V0. Okay, so that is minus 1 by 4 q minus 8 times norm V0 square. You see, but this is greater than or equal to 0. So this has to be greater than or equal to 0. This gives me a range for q, right? So that tells me q is less than 8. Q is less than 8. Okay. Of course, this is only one condition. I will look at all such vectors and then I'll have infinitely many conditions. But then, after a few computation, you will see that there is a common condition which is satisfied by q. Okay. So let us look at one more one more such thing. So I look at V0 norm square. So that is x alpha V minus 2, x alpha V minus 2. Right? Remember, x alpha pushes it to the right, right? So V minus 2 will go to V0. And you do exactly the same computation as earlier, but then this is minus x minus alpha, x alpha V minus 2, V minus 2. And again, the proposition earlier will tell me how this x minus alpha x alpha acts on Vn, right? So that tells me, so this is minus 1 by 4 into q minus 0, V minus 2, V minus 2. Remember, V minus 2 is non-zero, right? Because I have all the even integers, okay? So I have minus 2, minus 4, and similarly 2, 4h, which is minus 4 times q times V minus 2 square. Okay, so that is positive, this is positive. So that will imply q is less than 0. Okay, q less than 0. So here q was less than 8, here q is less than 0. Now you write down all the other, you will see that q has to be less than 0. Okay. So all the conditions put together will tell me that the range of q is less than 0. But then we are done, because if q is less than 0, it is one of the, so it coincides with the q value for either the principal series or the complementary series, right? And j pi is 2z. So for the complementary series, j pi is 2z, and for the principal series pi lambda, j pi is 2z. And the q value for these two put together takes care of minus infinity to 0. So as long as q is negative, we are done. So such a representation will have to be either a principal series or a complementary series. Okay, so this implies that pi is either a principal series pi lambda, or C, okay, complementary. Right. And so this you can do for any other representation. Okay, essentially, you will repeat this argument. The only, well, in fact, only for j pi doubly infinite, you have to do this. Okay, j pi, if it is one-sided, then you start from n plus 2, and so on. Since j pi is starting only from n, q value is already n into n minus 2, and that coincides with the q value for dn plus, and we are done, right? Similarly for dn minus. So matching it with discrete series is trivial, you don't have to do any computation. But for principal series, complementary series, you have to sort of look at the value of q by these kind of considering the norms, and say that q will fall into 0 to minus infinity to 0, and then match the k types, and then conclude that it has to be the corresponding representation. So this finishes the classification of the representations of SL2R. And in the next lecture, we will try to give the idea of Harish-Chandra and the proof of Plancherel theorem. Okay, so I'll yeah, maybe I will okay, I have some time, so I'll take 5 more minutes to sort of write it down. Okay, so Plancherel theorem. So we start with a unitary irreducible representation of G. Then rather deep theorem due to Harish-Chandra says that, so there is just a function. Well, it's actually a locally integrable function away from certain walls of the well chamber, but in this case, it's just 0. So there exists a function theta pi. This is the character of then trace of pi psi. So remember, pi psi is the Fourier transform, right? So this is integral psi g theta pi g. Okay, so remember pi psi is integral psi g pi g dg. Right, that's an operator that becomes a trace class operator And the trace of this is actually psi integrated against a locally integrable function. Okay, so you can think of it as a distribution acting on CC infinity functions. Okay, so let me write down the Plancherel theorem. So for n greater than or equal to 2, let theta n be the character of dn plus direct sum dn minus. So that takes care of all the discrete series, and theta lambda and theta lambda minus character of phi lambda, lambda in R, and phi lambda minus lambda in R. Right, so that takes care of all the representations. Complementary series does not appear in the Plancherel theorem. Okay, so then the theorem is for every f in CC infinity, 2 pi times f of E is the identity in the, so this is inversion at identity, summation n equal to 2 to infinity, n minus 1 into theta n of f. So theta n of f, I'll write down what that means. That is just the trace of the corresponding operator, plus 1 by 4 integral over R theta lambda. Theta lambda comes from the principal series. Lambda tan hyperbolic lambda plus 1 by 4 lambda minus, so that is the character for the other set of principal series, lambda cot h phi lambda by 2 d lambda, where, so I should write what is theta pi of f for a representation, that is simply integral fg theta pi g, right? Right, that is a trace of, so this is trace of pi f, right, the Fourier transform. And these functions are called the Harish-Chandra C functions. Harish-Chandra C functions. Okay, so this is what, well, I'll give a sketch of the proof in the next class. Okay, so I'll stop here.
So, thank you, Professor Narayanan. Any questions to ask or comments? If there is no question or comment, let us thank Professor Narayanan for this splendid lecture. Thank you so much.
Thank you. Yeah.
Thank you, Professor Muruganandam, for finding
Thank
time
you.
for this talk.
No, you gave me a chance to listen to Narayanan.
So I was giving you many chances, but you could.
It's a very clearly given lecture.
Yeah.
I always enjoy.
Okay, so I will log off because there is a talk at 4 o'clock.
Great.
Yeah.
I too have.
Yes,
Yeah.
yeah.